Alright, today we're going to be solving the bowlero equation. We have our givens here, our equations here, or not picture here. So as you can see, this is each event. Event 1, ball's moving at 1 meters per second at a height of 1 meter. Event 2 is when the ball is about to be released. And event 3 is when it is released and already moving and rolling. So we're going to solve for V2 and our V3 and rotational velocity right here.
You want to see it? It's kind of cute. It's got wheels.
And then also we're going to solve for...
You built a slingshot?
Do you need one?
Did you build one?
Well, we
the force of David on the ball.
Was it a catapult?
This is David.
I'll show you.
Alright, let's go ahead and begin and solve for V2. Or first, let's start our bar graphs.
Can you send us the blueprints?
No.
You have a screenshot.
We do. You can buy it off of him.
$10.
It was like 15, right?
That's not bad. Do you have it with you?
It might be my car.
That's freaking crazy.
I'll Apple Pay you right now.
Actually, I can't.
So these bar graphs represent each event. These bar graphs represent each event going on.
I have a friend.
Event 1, event 2, event 3. So event 1, as you can see,
has his own workshop in his garage.
mostly
And I was like, where'd it go?
gravitation.
That's what it looks like. It's got wheels on it.
Oh, so it's a launcher.
Event 2,
Yeah. And you can
about to
lock these
release,
wheels,
so
you
it's
can lock
mostly
one and
kinetic.
pivot it. Yeah. But go Home
Actually,
Depot,
all
some
kinetic right here.
2x4s for like $3.
This is right when the ball's released. Event 3 is when it's rolling already.
It's like, yeah.
Okay, we're gonna build. Let me take a picture of that because we're gonna build that.
So that's some energy in the rotational.
Like a catapult.
As you can see, we're using 5 blocks to represent energy
That's all
each time, and it's all conserved.
You have no copyright, right?
Oh no, I got
You guys talk a little quieter.
Oh, sorry.
Yeah, what are we doing?
So let's solve for V2.
Okay, let's go.
So this is basically V2 right here. So we can add up EG1, EK1 to equal EK2.
It's like one. Okay, so you're just. Are we getting his solution?
We can then sub in our formulas for each one.
Just like it's Saturday morning.
Alright. And then we see here that mass is in each of these, so we can divide mass out.
If you have it, then we'll buy it.
If it's not with me,
Addison, do you have the slingshot? Or is it with you?
no? Okay, so if it's not,
It's gonna look something like this.
If it's not, if
Now we can go ahead and just plug in our values.
okay, yeah. If it's not my car, we can keep it on. So we can go check it out. Let me just finish up with this one. I have to re-upload this.
After we plug in our values, we can solve for V2 by multiplying by 2 for each side.
So I've got it right here, so what part?
Simplify.
So this is the second law.
Take square root of each.
Those of you that have ever seen on anything I have.
And so all I do from here to here is I go over this and I sum the forces.
And we get 4.54 meters per second for V2. Let's go ahead and write that up here.
And that's going to be 4 mass times its acceleration. So it's 2 seconds.
And we can go ahead and erase this portion here.
Okay, so
Now that we've found V2, we can go ahead and solve for v3 and rotation or angular rotation or angular velocity 3.
Is by squaring what
See
the
that?
tangential velocity is. So at this point,
Why is it blurry?
before I
There we go.
deliberate, isn't the velocity VL, yeah, VL2, right? Because it was VL1 up here, and then down here is VL3. But this
To solve for each one, we can set it up as EK2 equals
that's tracking
EK3 plus ER3.
the acceleration
Just leave your phone here.
of an object that's moving in a circle, and this is 1 meter, right?
Plug in formulas for each.
So this radius of the circle is 1 meter, and its velocity is VL2. So the centrifugal acceleration will be VL2 squared over R. And, you know, again, if you want, you can look up, I'm sure somebody on YouTube has derived this, but it's something I gave you when I talked about rotation and circular motion.
All right. So once we get to this point, we can write out actually what these represent.
Move that to that side.
So I is 2/5 mr squared.
And then can't I plug this into that? And then I just pull the mass,
Times
since this isn't this,
angular or velocity, which is going to be
isn't the force
V over R.
on the ball, its mass times that gravitation.
And looking back at this, it's squared. So we square it. Now, as we can see here, we
So
can
that's
get
the
rid of
weight the ball.
the halves. Halves is in each one. And we can also get rid of the masses.
Okay. Sure.
And then when we get rid of the halves, we just basically multiply by 2 for each side. And then we see here that there's already something like that. So this is gonna have a 2 in front of it. You can rewrite this as, make it look a little better. From here, we can get rid of this, the R. So we're left with this. We can add these together, these V3s, to make it simpler. So it's gonna be 7/5. And now we can sum in our value for V2 squared, which is going to be 4.5 squared. We could just do that on a calculator. It's 4.54 actually. 4.54 squared is going to be 20.6116 equals 7.5 V3 squared. Multiply by the reciprocal to get rid of that. So it'd be that 20.6116 times 5 divided by 7. And then we should get something like this. take the square root of each side, we get 3.84. Alrighty. Now we want the rotational. So it's going to be V equals R times angular rotation. And let's see if can you see that in the, yeah, we can. Good. And all right. Yep. Good. 34.91. Rotations per second, or rad per second. So what I did here is I just plugged in the values for V equals R times angular rotation. Our V3 was this, so we put that there. Our R is given up here, and plugging those values in, we get 34.91. So we can write that up here. Also our V3, 3.84. Meters per second. And then now we can finally solve for our force of David on the ball. Let's write out a little diagram first for what this is going to look like. We got the ball being here, his arm. This is the path it's going to take, and we want to know the force is right at this moment. So as you can see, this looks like our second bar graph, or this picture right here when it reaches the floor. So then we have force of the earth on the ball down here, force of David on the ball up here. We want this one. So using this and centripetal acceleration,
Thank you for leaving it.
which is also here, we can go ahead and set up our equation.
Yeah.
Yeah, no.
I gave that to you like
Was that last
and
week?
I straight up forgot to get it back.
F
Yeah, cause I came back to class, and I was like,
equals
or the.
F. I'm sorry. Mass times acceleration, which is going to be our centripetal acceleration in this case, since it's moving in a rotational motion. So this is going to be gravity. We know that. And we also know what this is over here. So we can go ahead and plug in our values. Mass times, which we got V squared over R. We could do some simplifying here, but it looks easy enough to just plug in. V2, 4.54 squared over our R, which is gonna be 1 in this case because it's the length of the arm. That's what we're solving for, the force on David's shoulder, or the ball. Force of David on the ball. let's go ahead and get these values. 4.54. Get
Just pay $10. Pay $10.
5 times 9.
Dude, it's still not doing it. Dude, that's so crazy. Oh, thanks for Wi-Fi. Have you got to the end?
We can add our 49 over.
No. So I'm not gonna use the one for this time. Like, change it.
We should get
Are you done using this board?
force of 152.06 newtons. So for this problem, that is how you solve for our V2, our V3, and our angular velocity or angular rotation 3. That's how we solve for our unknowns, and also solve for the force of David on the ball.